And we are live on a Friday again. But what a good Friday to get together with. So, welcome. If you are new to this, you have just found ADRAMADA, another Dave Rush Ask Me Anything digital alchemy. We get together once a week, usually on Thursdays, but my schedule keeps me occupied on Thursday. Then we push it off to Friday, or we push it off to the following week. We do it at 7 p.m. Central Time, whether we are on Standard Time or Daylight Savings Time, which is coming up in 1 week. It's always 7 o'clock my time. So if you're used to watching this from overseas live at 7 p.m. Standard Time, after next week, it's going to be an hour later for you. Because it gets darker sooner here. So good afternoon, good evening, everybody, wherever you are in the world. I am the aforementioned Dave Rush, your tech from Texas, and this is ADRAMADA. Come for the shirt and stay for the news and the project. This shirt has been a challenge to find. I can find Galaxy Quest shirts, and you got to open up your wallet and hemorrhage Benjamins for them. But there was a sale at Woot a week or two ago. And yay! So I finally got a Galaxy Quest shirt. I'm a happy guy. Today is not. Hey, look at that typo already. Today is Friday, February 28th. This is the last day of February. And I didn't get today is noteworthy because I've been very, very busy all day. I beg your pardon. So, in addition to the show, I hope you're catching it live, and if not, I hope you're catching it on the archive, not too far into the future. We have a Discord home where everybody who hangs here and many other parts of the internetosphere in which I hang join up, and we got cool things going on over there. So just before the show started, about 10 minutes before the show started, I put links to everything I'm going to mention here. And I'll try to remember to do it at the end of the show. We got a long show, and I'm going to try and speed things up real quickly. But we've got a Discord server. I've given my contact information. If you ever want to email me, my X account, DRushTX, Mastodon, DRushTX at mastodon.social, and more. 2 weeks until Pi Day Friday. So even if I'm available on Thursday, I'm thinking about doing the show on Friday, just so it comes down on Pi Day, 3/14. Then we talked about DST. Last week, we did part 3 of 4 of our subnetting series. We started out with basic binary to decimal conversion, and then we moved to Classful network addressing. Last week, we got into actual subnetting, which is called CIDR. Classless Inter-Domain Routing is the official term for subnetting. It's subnetting. And we got through most of the background that we needed and the better part of one example. We're going to do another example tonight, summarize things, and mention 1 or 2 other cool things. It's going to be a fun show. Let's start with some slides. I'm going to power through, and then I'm going to catch up with everybody who's chatting and doing that kind of stuff. 12 years ago today, actually tomorrow, February 29th of the year 2012, the nice folks at Raspberry Pi introduced to the world the Raspberry Pi A. I am not the guy who lives and dies on cutting edge technology. I research it, I understand it, but I don't adopt it typically very quickly. But this was such an exception. Look at that handwritten on there, 2012, because I read about this thing and immediately ordered one of the first models. So this is the first Raspberry Pi Model A. not the car Model A. And I've used it. I've used it then. Something is not perfect with it. It was a new product, right? So there's bound to be issues. And one of the issues, you can't see the problem here, but it used a full-size SD card sticking up out of the back there. And the SD card no longer works in there. You can tape it down and, torque it in just the right way and put your tongue in just the right corner of your mouth and get it to work. But it's basically been relegated to my museum shelf. Basic facts of the thing is where we've come in 13 years. It had a pair of USB 2.0 ports, full-size SD card, a 26-pin GPIO. They've moved to 40-pin and more in the compute module. A 700 megahertz 32-bit CPU. I think we're running about 1.7 now, 1.7 gigahertz. 256 megs of RAM. They later came out with the A Plus model that had 512 megs of RAM. Full-size HDMI connector, 100 megabit RJ45 Ethernet. At the time, the OS of choice, and pretty much the only one available, was Raspbian. Raspberry, Debian. By the time they were done, all kinds of distros, including Plan 9. And I mention that because next week we have Ms. Hayes coming on to talk about Plan 9. It was $35. Entry models are still $35. All right, back to slides. Keeping it short on news in general, this is my latest snapshot of my pre-search node sitting on top of my desk. And a little over, it's about a year running. I took this shot yesterday. I think it's been running for 1 year as of yesterday. A little over 3,000 searches. And again, I don't know if that's good or bad or high or low, but what is it, 360 days in a year, 365. So that's a little shy of 10 searches a day that my little node gets. I've never monetized it, and I don't expect that that kind of search quantity would be worth much in a monetary sense, but it's cool. All right, official news of the week now. Let's do this. No, don't do that. Goodness gracious. Wow. Windows 11. Oh man, am I going to lose you guys? I may lose you guys. Because Windows 11 is doing funky, terrible video things. Alright, let's see what I lost and what I didn't. This is the COLA, with a K, entrance to hell. This is the largest man-made hole ever done. 12,000 meters, a little over 40,000 feet. They worked on it from the early 70s through 1989. And then they had to close it up because A, they ran out of money, but B, they found a problem. It got hot, really hot, much hotter than they ever expected at 40,000 feet. And the drilling equipment couldn't handle the heat down there. And so they closed the project. So that's been closed for 25, 35 years now. 3 years ago or so, a new project was begun to dig the deepest hole ever with the goal of tapping thermal energy, right? You get down there where it's nice and hot, you pour water in, steam bursts out, and we use steam. Because a lot has happened in 30 some odd years with drilling technology. For instance, energy-driven drilling, laser drilling, things like that. And so there was a report on this about 3 years ago on where they were at in a publication that called New Atlas. It's one of my regular go-tos for science news. And people write them all the time. Hey, you wrote a story on years ago. How about a follow-up? And this is one of the rare ones that they've elected to do a follow-up on. Where are we at now? So because of all these marvelous new technology developments, they are digging and they're shooting to break this record. They have a beast called a gyrotron, and they use millimeter wave energy beams. And what's interesting about all this is there's a bunch of it. One, who's interested in drilling? Well, people who want to get deep into the earth and tap geothermal energy. Also, petroleum companies, anybody who digs, especially anybody who digs deep. So they are helping fund this thing. They're going to benefit from it. You may or may not get into petro, fine, but it exists. Now, there's an interesting problem, or I don't know what, there's something interesting about it. If they drill a hole that, where's the numbers on this thing? Something on the order of 1 or 2 centimeters in diameter, they can pound through almost 300 feet a day. But as that hole widens out to a practical value, 4 or 5 inches, they're not getting that much. But compared to traditional drilling, no matter how you slice it, they are digging between 10 and 100 times faster than conventional drilling. So that's cool. The other cool thing is because they are using heat tools, one of the things that they can do is when it's time to stop drilling, take a break, fix problems, do whatever, they hit the area that they're working on with a super hot beam, and it glasses the material that they're drilling, and that self-seals the hole. So, fascinating technology, and that's why we're here. We like tech, you like tech. Last year, I reported to you, many people reported to many people, that we were at the end of an 80-year nova, semi-supernova cycle on what they call the Blaze Star, T Coronae Borealis. And it didn't happen. And there hasn't been much news about it. So I finally ran across news about it. They believe this is the year now. It'll be 81 years instead of the usual 80, where this star goes nova. It blows itself apart every 80 years or so and then comes back together and meshes back up and then blows itself again. And they're seeing activity on the star is the long and short of this one. Anything else? Yeah, I'm not going to dive deep into that. Let's talk computer-esque news. Oh! Where did that go? There was a piece in... Oh, okay, there it is. It's coming up. Network Manager. And that's a really funny slide because Network Manager as a program has no space between network and manager. It is the go-to network management tool case that lives in many, 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 many Linux boxes and has for many years. In recent years, the world has been moving toward an alternative called NetPlan. But there's a lot of reasons that a lot of distros continue to stick with Network Manager. If you are an enterprise installation with 1,000 servers, more, 10,000 servers, changing all of those things from Network Manager to NetPlan is certainly possible, but it's going to take time. There's going to be problems. And if everything's working and it's doing everything you need to do, it's if it ain't broke, don't fix it kind of situation. So the nice folks at Network Manager continue to develop and improve it so that people who have legacy Network Manager installations going can continue to use that and take advantage of new technologies. Sipping my soda there. So Network Manager 1.52 came out this week. And why do we care? Because it came with some major new improvements. I'm kind of surprised that it's a 0.01 release. It was a 0.02 release because the last release was 1.50. Now we're on 1.52. But they have released IP VLAN interface support. And I'll get into what that is. ETH-tool FEC mode, that's forward error control, which is a way of handling networking errors. It introduced IPv4 link local fallback. So if you got an IPv6 and something in your system says, I gotta have IPv4, network management says, don't worry, I'll create one for you for your needs. So that's kind of cool in Magic. What IPVLAN is it's a driver for virtual network devices. Basically, opens up the capabilities of a single network interface card to support many, many virtual network interface cards in virtual machines and things like that. That's really important in many of these environments where we've got systems running tremendous numbers of virtual machines. So that's a cool thing. About half my machines are on Network Manager. The other is on NetPlan, and I will be experimenting. I just read about this today. It's news to me. I posted this on the Discord server today. Microsoft is going to close Skype in May. They've had it for, I don't know, 11 or 14 years, something like that. I think they got it in 11 from, of all people, eBay. Peak usage on Skype was over 300 million, 330, 340, something like that. Last time Microsoft reported user numbers was in 2023 with just over 30 million, so about 10% of its peak. There's no information available on 2024 and 2025 users, but clearly they've been kind of run out of the territory by FaceTime and WhatsApp and Zoom and Slack and so forth. This is a screenshot of my Pi-hole that I took today. They've upgraded Pi-hole from version 5.x to version 6.x some months back. And this is not because I'm a late adopter, but when there's major releases like that, I won't be an early adopter. Way too many problems come up with 0.0 releases. But if they're on a 0.04 or something like that, yeah, 604. So I thought today was a good day to do that. And while I was looking around, it said, you've got 2 error conditions. I thought I'll take a look at those. I haven't looked into why and how, but they're fascinating. The 2 errors. One of them is a query from a non-local APIPA address, 169.254. So I've seen things like that happen before in Wireshark. I've seen things come across in my systems and other systems, and how that's happening, I don't understand very well unless it's an embedded payload. Almost surely that's what it is now that I think about it. It probably came in as an embedded payload on an IPv6 packet. And it did a query on my Pi-hole. So I need to do something to step up Pi-hole security a little bit. And I also got a rate limit error. A client in-house, 192.168.1.100. .100 is the last number in my DHCP scope. And I don't know what device owns that because I haven't bothered to check it out today. But it got rate limited. It was sending out so many queries that Pi-hole said, nope, I'm going to cut you off for a while. And it had sent 1,000 queries in 60 seconds. So that's a hack. Somebody's doing something. It might be malware that's sitting in there and got triggered. I don't know. But I find that one interesting. All right. That's it for slides until we get to project. I got 2 more little pieces of news. And then we'll check in with everybody. And then we'll get started on project a little early today because we got a lot of content. Okay, are they both space news? Yeah, they're both space news. Once again, NASA has changed its projection about the chances of Y24, I get the name right this time, hitting in December of 2026. You'll recall it's gone all over the boards from 1.8, 2.3, 3.2, back to 2 point something. And now a week later, the latest observation says 0.0004%. Sorry, anything that changes that dramatically, that quickly, I'm just going to call that a bubble of news that will surely change because it's still outbound. Also, tonight, this very night, as we sprechen, 5 planets will align in our solar system, Earth being one of them. So you'll only see 4 unless you look down at your feet. But that is all the news that's fit to print. I'm not going to dive into that. Easy research for yourself. All right, let's see who's here and what you're doing and what I'm doing and what anybody's doing. Change the system around. I don't want to lose anything. There we go. What are you doing? What you're doing? Strange stuff. All right. So as ever and always, Tullowitt gets in here 5.5 hours before showtime. Shia Moonstone, great to see you back in the fold, and I saw you were very busy on Discord today, getting caught up. Good for you. Thank you. And good afternoon, half an hour before showtime. Were you guys both sitting there? Hey, by the way, just before showtime, I checked the thumbs up. There's still only one, and we got people here. I got 8 people. Give me some thumbs up, huh? Not because I need it. The show needs it. All right. I posted all of my how to get in touch with me's and told you about that. I'll do that again later. Patricia has changed her name once or twice in here. Hi, Patricia. I know you just go by Patricia, so we can ignore last names, whatever you got in there, and middle names. So you just finished catching up. Yeah, thank you for the nice comments on the show. You know, I know this is niche, but I've got it targeted for a specific group of people. And again, this is sort of a first pass that I think I can turn into, once I pull these out and edit them a little bit, into a nice 4-part series. So for anybody who wants to learn subnetting IPv4, this is going to be an excellent learning tool, I hope. So yes, great to see you live again too. Hope the dinner with your stepdaughter went well last weekend. That's fun. Woo! I guess that means we were on, huh? Let me switch accounts. We are in fact live, joining my new system. On my new system, got a new system. Cool. Can't wait to hear about that. Double woot. And applause. And Joey Quetzal is here. Exception. I live to be the exception. Jason's Hill here. So cool. We're all in on time. You set an alarm. Me too. I had a lunch meeting today with an old coworker. Not one you know, but the company you do. And I haven't purposely busted keto in 2.5 years, maybe 3. And there was just no other choice other than starve, and I don't want to starve. So we went to a brew pub, and I had a burger without a bun, and it came with a serving of fries. I haven't had a French fry in over 2.5 years. I ate the whole serving of fries. I am now kicked fully out of keto. It's going to take me a week to get back in. I'm going to have to work out 2 times a day, every day for a week. Ugh. I was a niece's daughter who turned 20. Okay. Yeah, okay. Tell me about feeling old. All right. Well, we are in part 4 of 4 in subnetting. So we started out with basics. Here's a binary number, converted to decimal. Here's a decimal number, converted to binary. And we got good at that. Doesn't take long. It's an easy to gather skill. The following week, we started Classful IP addressing. And Classful IP addressing simply means use the default subnet mask that comes with a Class A or Class B or Class C network address. It's Classful because we use the old class methodology. And it's easy to use, it's easy to understand, but it's got problems. And that is usually those networks are too big for any organizational purpose. So they invented for us classless inter-domain routing, subnetting, the ability to take a single network with a single network address and break it up into multiple subnets, which I'm going to call chunks, back and forth, and finally we'll get done and we'll exclusively use the correct term. A hiccup again. And so we started on that last week. We got into classless inter-domain routing, and basically what that means is we don't use the default subnet mask. We extend the subnet mask into host bits, and however many bits we've extended that into, we can treat those bits like network addresses, subnetworks of the network address. And so that's where we're going to pick it up. We did an example, nice and slow. I'm going to do another example today. We're going to move through a little bit more quickly, but not tons more quickly. So here we go. This is a refresher on the process, which I have broken down into 4 steps. The first one, we ask or answer a question. How many network chunks, subnetworks, do I need? And we come up with some answer. It might be 6, it might be 8, it might be 2, it might be 40, whatever you got. Whatever that answer is, then we have to figure out the minimum number of bits necessary to arrive at that number. So let's say that we need 6 networks. Well, that takes more than 1 bit, because 2 to the 1th is 2. I can make 2 networks if I mask off 1 bit. How about 2 bits? 2 to the 2nd, 2 raised to the number of bits, that's 4. That's not enough networks to get to 6. How about 3 bits? 2 to the 3rd, 2, 4, 8. 8 is more than 6, so that's the minimum number of bits that I need to count to achieve at least 6 or at least 8, 2, 4, 8 chunked subnets. And then I'm actually going to do that borrow process. I'm going to borrow the 3 bits that I say I'm going to need to make subnets. And what we do is we borrow them from the left side of the host of the first host octet. And by borrowing them, what we do is we simply take the default subnet mask, which ended at the network address ordinarily, and now we're going to extend it over the first 3 bits of that first host octet. And that's what tells my computer and the router and everybody else who gets the same extended subnet mask to start looking at host bits, and 3 of them, in fact, the first 3, and start treating them like they were network bits. So that's step 3, borrow the needed bits from the left side. How do we do that? We extend the default subnet mask over the borrowed bits. And then finally, we crunch the numbers. We find out, okay, based on that, what are the subnet addresses that are valid, and what are the valid host IP addresses that are valid? Valid that are valid. Easy for me to say, huh? Don't panic. I know you don't have it yet, but you've heard the terms. We've seen these 4 steps. We're going to see them again. Here we go. I know this is a very busy looking slide. Again, don't panic. Why is that there? I never did fix that slide. I gotta do that. Slide 29. But this is the slide that we left off on last week, and I'm not going to do that here. So what we're going to do is we're going to dive right into okay. I made lots of new notes today and lots of new slides, but I didn't fully review these older slides. So. Slide 29. Determine the host count and assign ranges. That needed to be fixed. Enumerate the subnet addresses. Okay. All right, so we've got a subnet here, and I can tell that because if I look at the top of the slide, I see 3 octets that have all 1s in them. Since all of our examples so far have been Class C, that's a default subnet mask. But look at this. It's got 3 bits that extend into the 4th octet. So that tells me that my new mask is no longer a WAC 24. It's a WAC 25, 26, 27. Ha, typo on that slide too. Fix this slide. So that should be a WAC 27. And what I'm going to do is I'm going to treat, as a result of this subnet mask, the first 3 bits of the host octet as if they were networks. So I can set the first 3 bits to 000, 001, 101, 110, all the way up to 111. And we go back to our first week of this series and say the first column is the 128s column. The second column is the 64s column. The next column, the third column, is the 32s column. Every place we have a 1 is going to tell us the value of that subnet mask. So the first example that I have on that first row, 240.80.70. Some zeros. They're always zeros because this is a network address. I got zeros under the first 3 bits of the 4th octet. That means it's going to be on subnet 0. 0 times 128 plus 0 times 64 plus 0 times 32 is 0. So this becomes subnet 0. The next one, 001, there's a 1 in the 32s column and not in the other 2. So this is subnet 32. Moving down a little bit lower, 101. There's a 1 in the 128s column and a 1 in the 32s column. We add 128 and 32 and find out that this is subnet 160. And I have all those breakout examples here in the little red box on the right-hand side. So if I mask 3 bits that are normally used for IP host addresses and turn them into subnet addresses, I have to enumerate the values of each of those subnets. Ooh, did that. Notice also that to the right of those subnet bits are the rest of the host bits. And we mentioned this before, you can't have host bits that are all zeros, and you can't have host bits that are all ones. But anything in between is fair game. So I've got 5 host bits left here. So on subnet 000, subnet 0, I can have any value after that from 00001, not all zeros, but the first one after that, through 11110. I can't have all ones. And that's 2 to the 5th minus 2. There's 5 positions there. And that gives me however many addresses that is. 30. Did I steal 3 there? 62. All right. Again, not to panic. We're there. So this is a blow-up of what I did and a little bit of an explanation. So we've expanded my 4th octet here, so my screen isn't quite so busy. Here is, on the left side, the extended subnet mask that goes over the first 3 bits of the 4th octet. There's my 128s column, my 64s, and my 32s column to the left of the vertical line, and then the rest of the columns, 16, 8, 4, 2, and 1, on the right. Those will be traditional host bits. There we go, 30 hosts per here. So if I look at 000000001 through 0001110, there's 30 possible values there on subnet 0. So my range is 1 through 30. Next one, we increment the subnet, put a 1 in the 32s column. So moving over to the right of those 2 sets, we see this is subnet 32. It still uses the same 5 bits for host bits. Look at the top of the number of hosts column. We use that formula, 2 to the 5th minus 2. That tells me how many hosts are on this subnet. There's 30 hosts on subnet 32. There's 30 hosts on subnet 0, 30 on 64, and so forth. And so then we have to figure out what the host addresses are. And what you do is you look at all 8 bits and pick the first legal one. There's a 1 in the 32s column and a 1 in the 1s column. So that means the first legal IP address here is 33. And then we look at that second set, 001, 4 1s and a 0, add up all the columns that those have 1s in, and we're going to come up with 62. And I want you to notice a little pattern here. If you look at the range column on the far right, the last legal IP address is 30. Go up 3, and that will be the first legal address of the next subnet. That gets rid of the all 1s that would come after it. That gets rid of the all 0s that would come after it. So that would, or yeah, all 1s and all 0s, which would have been 31 and 32. So, there's 33. And then I got 30 possible values, 30 possible hosts in here. So all I have to do is add, actually 29. So 29 and 33 is 62. That pattern continues down to the next row. Subnet 64, I go up 3 from 62 to get the first legal host address is 65. Add 29 to that, I get 94. You get the idea. Slide advancement. So here's one more little factoid. Makes life a lot easier. You can do this, you can calculate this manually back from our first session on this, but this tells me if I mask a certain number of bits, how many subnets I will get out of that. So if I were to mask the first bit of a host octet, I would get 2 possible subnet addresses. 2 to the 1th is 2. That would be a 0 or a 1. Those are my 2 possible values there. And then I have, if this is in the 4th octet of a class C, I got 7 bits left to work with for host bits. So we use the formula we mentioned the other day, 2 to the 7th minus 2. That means on each of the 2 subnets, I can have 126 hosts. If I mask 2 bits of a host octet, extend my subnet mask over 2 bits, I can make 4 subnets out of that. 00, 01, 10, and 11. I got 6 bits left to work with for host addresses. I use my formula, 2 to the 6th minus 2. That tells me on each of my 4 subnets, I can have 62 hosts. And you keep on cranking down. Let's go look at if I mask 5 bits. 2 to the 5th is 32. I can make 32 subnets out of that, but each of my subnets, after I do 2 to the 3rd minus 2, will only have 6 host addresses. How about we mask 6 bits? 2 to the 6th, I get 64 subnets, but there's only 2 bits left to work with. Each subnet will have 2 possible hosts on it, and one of them is going to be the router, because the router on subnet 6 or subnet 64, he's got to have an IP address, the first legal one. And then when we start screwing around with masking off everything except the last 1 or 2 bits, it might be possible. You can mask 7 bits and leave 1. Technically, that leaves 0 host bits to work with. After we do 2 to the 1 minus 2, there's 0 host. But it has a special case use, and that's cool. If you mask all of the bits of the host octet in a class C, you come up with -2 possible hosts, but 256 networks. And it's not practical, it's not real. But there's still something we can do with that. So I'll get to that again. All right. Let's find Jill in my notes. This is all the new stuff. Slide 33, Class C example. So we're going to do a second example here. I'm going to do another Class C address. They're the easiest to understand as foundations, and then when we get all done, I'm going to talk about Class Bs and Class As. So this is my friend Jill. Jill's got a single Class C network address. It's 197.40.12.0. It's a standard Class C network, so it's got a WAC24 subnet mask. She needs to create 3 subnets. This is the assignment that came from on high, and her subnet has to support at least 10 hosts per subnet. So we got to find, first of all, the ideal mask to pull that off. Here's our 4 steps. Step number 1, we answer the question, how many subnets are needed? And we got that answer from on high. It's 3. And I added this little extra piece in it for people who are going to take, I don't know, some certification exam, because this is always another factor going to add into that. So Jill needs 3 subnets with 10 hosts per subnet. And she's got this network address to work with. It's a Class C 197.40.12.0. It's a WAC 24. So if we look at the binary version, up on top, all my 1s, that's my subnet mask. 8.1.8.1.8.1s. That's 8.16.24. That's a WAC 24. And we also know that 8 1s in an octet are 255. So 255.255.255.0. There's our default subnet mask over a decimalized IP address. So now what I'm going to do is I'm going to forget about the actual network bits. I don't need them to calculate subnets. So I'm just going to move this 4th octet down here and blow it up a little bit. We dump the network bits, the real network bits, and we're going to focus on the host bits. So this is the same slide we saw a minute ago to help us out. Jill needs 3 subnets. If I mask 1 bit from the first row, I get 2 subnets. That's not enough to meet Jill's requirements. But if it was, I could have 126 hosts per subnet, and that meets her 10 rule. So what happens if I mask 2 bits? Well, 2 squared is 4. Hey, that's more than 3. That's good for Jill. I got 6 bits left over. That gives me 62 hosts for each of the 4 subnets. That's more than 10. Cool. 2 is going to be my answer. I could also pull it off with a 3. I can mask the first 3 bits of the host octet. 2 to the 3rd gives me 8 possible subnets at 30 nodes per subnet. But I got a bunch of wasted networks here. If I only need 3 networks, then what am I going to do with the other 5? They're just going to lie fallow, and I'm losing the benefit of the higher numbers of host addresses later on. All right. That's a useful slide. And except for fixing slide 29, these will all be ready to go, and I'm going to have them up at the ADRAMADA Discord server. You can download these. You can watch them while I do this, and I will, again, turn this into a regular course. You'll be able to download the whole course or stick it up on the net someplace. All right, so now I've figured out how many bits that I have to mask to make 3. Actually, I'll get 4 subnets out of that. I've got to mask 2 bits. So we're going back on this first row. This is step 3. Borrow the needed bits from the left side of the leftmost host octet. There's only 1 host octet in a Class C. And how do we do that? We do that by extending the subnet mask from being a WAC 24 to being a WAC 26. So the first example here is the default before we started messing around with it. It's a WAC 24. There's 24 ones, 255, 255, 255.0 over a Class C address, 197.40.12. And now on the next row, we extend that from being a WAC 24 to being a WAC 26. So now I've got a 255, a 255, a 255. And because I've extended the mask over the 128 column and the 64 column, that's a total of 192. So the decimal value of my mask is 192. I can express it as a WAC 26 because there's 26 ones working left to right. I can express it in decimal as 255, 255, 255.192. So again, I'm going to throw out the network bits. I don't need them. I just brought them in to remind you that's what we were working with. So why is the mask 192 in the 4th octet? Because the masked bits are in the 128 and 64's column. So down here in the very bottom, we see that 192 which is also expressed as .11000000, and that's what we'll be working with. So now what I'm going to do is I'm going to take those borrowed bits and I'm going to write down every combination of 1 and 0, and then I'm going to convert them to decimal. So I'm working with the 2 leftmost bits of the host octet. And the first 2 bits of that could possibly be 00, could be 01, could be 10, or could be 11. And when you tally up the ones under the columns, we find that that first one, 00, is on subnet 0. It defines subnet 0. 01 makes subnet 64. 10 makes subnet 128. And 11 makes subnet 192. How do we know how many hosts can exist on each of those networks? Well, there's always, for all 4 of them, 6 bits left. So we use our host calculator formula, 2 to the 6th, and then subtract the 2 illegal values, all 0s and all 1s, and each of these can support 62 hosts per network. And then I finally say, all right, now I'm going to write down all the possible ranges from here. So on subnet 00, the first 2 bits are always going to be 00. The next 6 bits are going to be 5 zeros and a 1 through 5 1s and a 0. So I wrote those down in the host range, and then in parentheses, I put their decimal values, 1 through 62. Do the same thing for the next subnet. On subnet 64, the first 2 bits for anybody on subnet 64 will be 01. And then the legal range is 5 zeros and a 1, or 5 1s and a 0. Decimalize those into 65 through 126. And do it again on subnet 128 and do it again on subnet 192. So this is step 4. Determine the number of hosts and assign the host address ranges. We're done. We're done calculating. Now we just got to sit down at computers and start plugging them in and assigning IP addresses to router interfaces and to host interfaces. I'm going to show you that in a few momentos. But that was our 4 steps. How many subnets do we need? How many bits does it take to make those subnets? Extend the subnet mask over the number of bits that we determined in step 2. And step number 4, enumerate everything. So we can start assigning them. We can hand them out and, here's a piece of paper, Fred. Take all the computers in accounting and give them an IP address in this range, log them, make sure we know who's got what. Cool beans. So here's the same slide with one more piece added to it. I don't think I did a dedicated one on that. No, I didn't. So what we've got here is, the top box is a router. And the job of this router is to manage all the subnets on network 197.40.12.0. So we said there's 4 possible subnets. Jill only needs 3. But my router's got 4 interfaces, and I'm going to have one that's left over for expansion later. So coming out the left-hand side, we're going to have a network interface with an IP address on subnet 0. Now let's keep working our way across the right. Then there's going to be a network interface on subnet 64. And a third interface in this router, it's going to be on subnet 128. And a 4th one that we're not going to use right now. Jill says I don't need it yet. But it's going to be on subnet 192. What that tells me, go back to the left-hand side, is anything that's on subnet 0 has to have the first 2 bits of its 4th octet set to 00. Moving over to the right, anybody that's on subnet 64 has to have an IP address in the 4th octet that starts with 01. Moving over to the right again, third interface, anybody who's on 128, including the interface in this router, has to have their first 2 bits of the 4th octet set to 10. And over on the last subnet address, 192, everybody who's on this router, who's connected to this interface, has to have their first 2 bits of the 4th octet set to 11. So what I've done here now, under the 0 and the 64 and the 128 and the 192, I've assigned a particular IP address to each of these interfaces. Thank you, Patricia. I saw that come scrolling by. No, I'm just going to fix the slides. But this slide is perfect, so I got no problems. I only have slide 29, is the, and there was one other one that had a really minor problem. But I will get those fixed. All right, so the IP address of this leftmost network interface card, we start out from the top of the router here, 197.40.12, and then it's going to be .1. It's on subnet 0, followed by a bunch of zeros and a 1, so he's .1. The second interface being on subnet 64, he's 197.40.12 dot. There's a 1 in the 64 position and a 1 in the 1's position. That makes .65. This is called the first legal address. In the 128s, first octet is going to have a 1 in the 128's position and a 0 in the 64's position and a 1 in the 1's position. So that puts them on, gives them IP address 129. And you can see what we did there. The last one, he's going to get IP address ending in 193, 197.40.12.193. So this router can route across subnets. All we have to do is tell the router that the IP address on the first interface has a subnet mask of WAC 26. Same thing for the second interface, same thing for the third interface, same thing for the fourth. Now he looks at that and says, oh, I see. I will treat those like they were networks. I'll treat them like they were network 0 and network 64 and network 128 and so forth. Back to the left-hand side, I connect that router interface to a switch. And to that are attached a bunch of hosts who will have final addresses .2 through .62. I take the second interface, working from left to right, hook him up to a switch, hook up a bunch of hosts to those switches, to make sure that all of those hosts are on subnet 64. They will all have 01 as the first 2 bits of their octet. And we can't use the 1 anymore. But anyways, it's going to be 66 through 126. That's when we did these calculations in the table in the middle of the page. Same thing for the host on switch 3, 130 through 190. And the host on switch 4, 194.254. That gets a little deeper into the weeds than we need, but I wanted to cover all the bases here. And we have. So let's review the 4 steps with 4-part harmony. No longer do we use the word chunks. So step 1 in the 4-step process of subnetting, determine how many subnets you need. That's not a technical calculation, that's an administrative calculation. We're going to organize our group into 5 sets of people, or five subgroups, or whatever the case may be. Figure out how many bits are necessary to create that number of subnets. If we need 5 subnets, 2 is not going to be enough. I'm going to need 3. If I need 10 subnets, 3 is not going to be enough, because if 2 to the 3rd is 8, that only makes 8 subnets. I'm going to have to mask 4 bits. 2 to the 4th, 2, 4, 8, 16. That's going to give me 16 subnets. I only need 10. 6 of them are going to be wasted. That's the nature of subnetting. All right, after step 2, now, having determined how many bits I need to borrow them by extending the subnet mask from the default that many bits into the host octet. How do we borrow them? We extend the subnet mask. And then finally, enumerate everything that you've done so that you've got a step-by-step map for doing this. All right, 2 more things to know, and that winds up our slideshow. We get done on time and a little bit of time to spare. I changed color for cool and new things. Everything that we've done here has been done on a Class C network. It's very easy. That's what the world teaches this, and I agree with that method. Because it's not confusing. We've got 1 octet to mess around with host bits. The problem with that is you might not have enough bits to make enough subnets with enough hosts per subnet on there. So in that case, we might have to start working with a bigger network, a Class B or a Class A network. And this slide is going to tell us everything we need to know about either of them. Up on the top, I have a Class B network address, 188.55.0.0. The second number falls, or the first octet falls between 128 and 191, so it's a Class B. And the default subnet mask for a Class B network is WAC 16, 255.255, or a set of 8s and a set of 8s, a set of 8 1s and a set of 8 1s. And that means the network address is wherever the 255s are, so the whole network address of this Class B is 128.55. Circular trip that we just made. I have 16 bits left over that I could use for subnets. And what's very common to do on a Class B network is to take the third octet, the first of the two host octets, and mask the whole thing. So now I've got what was a WAC 16, now I've made it into a WAC 24. And the last octet can all be subnets, everything through 000000000 through 11111111. There's 256 possible subnet addresses that result from that. And each of them has 8 bits left for node bits. 2 to the 8th is 256 minus 2 is 254. So I can have 256 subnet addresses by extending my subnet mask into the first octet, host octet, and each of those would have 254 host addresses. Nice. And you can do it a little smaller, you can do it a little bigger, however many networks you're going to need, and make sure you've got enough hosts per network when you pull that off. How about a Class A network? This first guy's a Class A network because his first octet falls between 1 and 127. It's 39. Okay? The default subnet mask of a Class A network is 255.0.0.0, which is 8 1s.24 zeros, or WAC 8. And that means that whatever octets the 255s are over, that's the network address, 39.000. So with this guy, I got a lot of masking potential. I can mask just the second octet, the first host octet. I can mask the next 2 octets, the second and third. Those are all host octets. I could even dig further into the 4th octet. So you might, or a little less. I don't need the whole first octet. That'd be kind of crazy because you'd have so many bits left over for host bits. But that's the drill that's explored down here. If I just mask off the second octet, the first host bit, I make a WAC 16. That would make 8 possible subnets. 2 to the 8th is 256. And there's 16 host bits left. 2 to the 16th minus 2. Each of those 256 subnets could have 65,534 hosts per subnet. How about I mask the second and the third octet? Now I've got 16 masked bits. 2 to the 16th is 65,536 subnets. And each of them has 8 bits left for hosts. 2 to the 8th minus 2 is 254 hosts for each of those 65,536 subnets. So moving from a Class C example to a Class B, you just apply the same rules, and it's really, really easy. I got 1 minute to go. Stick with me for 3 minutes. I only have 1 slide left. And I just want to mention this guy, supernetting. Supernetting is the opposite of subnetting. In subnetting, we take one network address and we break it up into multiple subnets. Supernetting is when you do the opposite. You take 2, and they must be sequential network addresses. You can see my example here, 192.168.1.0 and 192.168.2.0. And instead of extending the mask out to the right, we shift it 1 bit to the left, and that takes what was 2 networks and converts them, combines them into 1. And then this is our last slide, the final review. You've seen this 3 slides ago. I didn't know how long I was going to take on that. So answer the question, how many subnets do we need? How many bits are necessary to make that many subnets? Borrow the subnets, and don't forget, leave enough bits to have enough hosts per network. That's important on the CompTIA Network Plus exam and on the Cisco network. On CompTIA exam, they only do Class Cs. On CCNA Cisco exam, they use all of the possible classes. You never know what you're going to encounter there. And then move your subnet mask to the appropriate number of bits, and then start enumerating, and then you start plugging those values in. All right, we've done. Slide down here. Next week, so far Thursday, Maxine Hayes to talk about Plan 9. It's an internet. It's a Linux flavor. That's going to be fun. She has some really interesting insights on that. I'm stoked to look at it. Let me see your last, what you guys have been typing up here, and then we will close down right on schedule with everything done. You might download this video series and stitch the subnetting parts together. Yeah, let me make sure I got the corrected slides so you can have those. Maybe add captions for typo. That's why I see where you're going with that. Thank you very much. You can do that. But again, I'll have correct slides. You can do take stills and insert them. That's what I'm going to be doing. It's a good series. Thank you, Patricia. It is super useful. Appreciate that. And way to go. Thank you, Shia. Buzz, grind, Shia. Good course. Thanks. I've watched a lot of subnetting tutorials. Oh, this is by far the best. I think so. But, it's a different approach. I care more about the process than the what's, wherefores, whys, and internals until we get to the end and we tie it all up in a bow. So, let me do this. Bump. Next week, so far Thursday. Oh, it's always subject to adjustment because I got a guy and he kind of controls my schedule on these gigs. But until next week, whatever happens, as ever and always, I wish you a great rest of the week. Take care of each other. Take serious steps to stay healthy. And if at all possible, call or visit your parents. And never forget, technology is great, but the greatest resource we have are you and I. And with that, good night. I'll see you on ADRAMADA next Thursday on the other platforms that I'm on. Until then, remember, how you do anything is how you do everything. Eat, hop, pork,